Now that we are good at finding horizontal and vertical asymptote of a rational function, we're going to do some other functions that's a lot more tricky. And so we're going to find the asymptotes when different parent functions are combined together. And that can get really, really tricky. So what we want to do is use something called check the dominance of the function. So dominance of the function means what is going to dominate when what happens. Okay, so let's think about three kinds of functions. So let's think about exponential, polynomial, and logarithm. Okay, so exponential function means that something that has x in the exponent. So like e to the x, 3 to the x, 2 to the x, etc. Polynomial means anything that is a polynomial, like x squared, x cubed, x to the 4th plus 1, something like that. That's called a polynomial. Logarithm is just log x. It could be log base 3x, something like that. So these are the three kinds that we're talking about right now. So exponential function, if you remember, they all look like this in general, if you don't put any kind of transformation on it. Polynomial depends on the degrees, right? So if it's second degree or even degrees, it would eventually look like this, something like that. If it's a odd degree, it could just look like something like that. Logarithm always looks like this. Okay, so let's kind of remember these three things. So then what we want to do is think about dominance. Dominance of what happens when x is going to infinity. So when x is going to infinity for all three functions here, the question you ask yourself is which one will be the biggest when x is in infinity. Remember, we're talking about infinity, not like x equals 10 or x equals 100, because they could be very, very similar to each other when x is in very kind of reasonable number. But when x is in infinity, what number is bigger, or which function is going to be bigger? So let's think about it. When you put in x equals infinity, so let's just say x is like 1000 or something. So let's say you compare this one to this one to this one. I don't know. I'm just randomly picking these functions. So 2 to the 1000 compared to 1000 cubed compared to log 1000. 2 to the 1000, I don't even know what that is. It's a very large number. I should probably try to figure that out. Okay, 2 to the 1000. Oof, calculator says overflow. So very, very large number that the calculator cannot even figure out. 10 to the 1000. So 10 to the 1000 is 10 to the 9th. Log 1000, so this is a log base 10, so that actually tells me it's 3. So you can see that this is going to be bigger than that and then bigger than that. And that's because when we put in a very, very large number, this is what would happen. And so this is the dominance that you need to remember. Exponential is bigger than polynomial, is bigger than logarithm. So this is when x is going to infinity. What happens when x is going to negative infinity? When x is going to negative infinity, well, let's see. When x is going to negative infinity, and logarithm doesn't even go to negative infinity. In fact, it can't get past 0 in the parent function. So you can see that when it's going to negative infinity, polynomial is going to go straight down. or straight up. Either way, it's going to be much bigger than exponential because exponential is going to go to a flat line. And so when it's going to negative infinity, we would say the polynomial dominates the exponential. And then logarithm doesn't exist. Because you can't put any numbers that's smaller than 0. So we're going to use that to help us figure out the limit. So for example, let's look at this one. First, you got to check what x are they talking about? Where are we finding the limit? This limit is going to infinity, so then we will use this trick. If x is not going to infinity, it's going to a number, then what's the first thing you do? You plug it in, just like what we talked about before. So make sure you read the question very carefully. Is it asking you to find a limit when x is going to infinity, negative infinity, or something else? Because every situation requires a different trick. Okay, this one is asking for infinity, so we're going to check. So in the numerator, that is a polynomial function. I know it's a constant, but constant is kind of like a polynomial function. In the denominator, we have an exponential function. The exponential is, so we are looking for x going to infinity. X going to infinity is the first case when x is approaching infinity. So then we follow the rule of dominance. Exponential dominates polynomial, dominates logarithm. So then we know that this exponential is going to dominate the polynomial, which means it's much, much, much bigger than the 3 when x is going to infinity. Therefore, this limit is 0. Okay, so let me explain again. When x is going to infinity, the dominance is exponential dominates polynomial, dominates logarithm. So we know the bottom is going to expand so big, so much, that the 3 is non-existent in comparison. So then the bottom is like a 2-3 million, or even more than that. The numerator is still at 3, and therefore the number is almost like 0, is what we're saying. All right, let's try another one. Let's try one that doesn't have a square root. Okay. They're all square root. So let me try this one then. Square root ones are a little bit trickier because of the square root nature, and I'll tell you why. Okay, so in the square root issue, let's look at this limit. This limit says x goes to infinity, so we're still good. We're talking about dominance again. When we're talking about dominance, we are looking at not only just the top versus the bottom. A lot of times when the top or the bottom is composed of two different functions, we need to kind of split them. So let's kind of think about it. 3x, think of it as one function. Okay, so 3x, think of it as one function. 5 is another function, or you can think of it minus 5. It doesn't really matter. So if you think of 3x and 5, which one is going to dominate when you go to infinity? Well, that's obviously going to be 3x, because 5 doesn't change, right? When you're going to infinity, and 3x would just be 3 times infinity. So that's very big. You're just saying which one is bigger. That's the only one I'm going to keep. The other ones are so irrelevant, I'm going to get rid of it. So the denominator is going to look like a 3x. In the numerator, let's just ignore that square root for a minute and just look at 2x squared plus 1. So if you again split it into two functions, 2x squared versus 1, which one's going to dominate? Obviously 2x squared, because 1 is just a constant. It's irrelevant in the long term, so we get rid of it. So really this limit looks like square root 2x squared versus 3x. So then you ask yourself, which one is going to be bigger to kind of figure out the limit? Well, this one's a little bit tricky, so here's what I do. I simplify the numerator. So this becomes square root 2x over 3x. Okay, and then now that I look at this, you can see that this is really just a rational function with the same degree. So that is case number 1. So then the ratio of the leading coefficient, square root 2 over 3. So the limit is going to square root 2 over 3, or the horizontal asymptote is at square root 2 over 3. And this works because x is going to infinity. Now I'm going to show you a case when x is going to negative infinity, and that is something different. Let's try this one. Okay, so when x is going to negative infinity, again, you look at the individual functions in the numerator or the denominator, and then you ask yourself which one is going to dominate in the long term. And we say long term because x is going to negative infinity. And so this 3 is irrelevant. X squared versus x is irrelevant. I know that there is an x, so you may feel a little bit uncomfortable getting rid of it, but eventually square is going to expand so much faster than first degree, so then we just don't care about the first degree. All right, so rewrite this if you want. You really don't need to. This becomes x over square root of 9x squared. And then so this again simplifies to x over 3x. Okay, now you may be tempted to say that the limit is at 1/3, but it's actually not true. And why is it not true? Because the negative infinity. Why is that? So if we kind of go back to here, when we plug in a negative infinity, we would get negative infinity over square root of 9 negative infinity squared. And then so that becomes negative infinity over 3 infinity. Okay, why didn't I write negative infinity? That's because we have to follow the order of operation, right? We would square it before we square root it. So then the squaring it took off the negative sign. And then so it became a positive here. And so what happens is that there is this negative that we had to consider. So then the limit is actually negative 1/3, not 1/3. So what I'm trying to say is that when you have a negative infinity situation and you have an odd degree that is outside, then the negative needs to be carried with the odd degree because you're actually going to negative numbers. So then this odd degree is going to cause it to stay negative. So please, please, please be careful of that. Okay, let's look at some other situation. Let's try something weird. Number 5. So when x is going to infinity of this, again, because it's going to infinity, we're just looking for the function that will dominate. So get rid of this, get rid of this. So really the limit is x goes to infinity of square root x cubed over square root of 4x cubed. Square root of x cubed is a little bit awkward. We want to write it in a simpler way. We can write it as 3 over 2. Square root of 4 is just 2. I'm going to write it as 2, and then x to the 3 over 2. This is going to infinity, so I don't have to worry about the sign. The degrees are the same, so they cancel, and so then the limit is 1/2. So we'll be practicing a lot more of the limit in class, so I'm going to just show you the last trick to find limit. The last thing we're going to do is call something called a change of variable. So what that means is we can't really find the limit, so what we're going to do is just change the variable in hopes that we can find the limit a little easier. So the first one, limit as x goes to 2 plus of arctan or arctangent of 1 over x minus 2. Let's recall what arctan means. Arctangent just means inverse tangent. So what we're trying to do is figure out what limit x goes to 2 plus of tangent inverse of 1 over x minus 2. Remember, the first thing you want to do is just plug in. If you plug in 2, you're going to get 1 over 0. That's undefined. And so inverse tangent of something undefined is going to be impossible to find. So what we want to do is actually do something different. And so what we're going to do is think of this inverse 1 minus x minus 2 is really like a composed function, a function inside the other. And so we're saying that f of x is inverse tangent, and then g of x is this 1 over x minus 2. So we have two functions that's composed together. So what we're doing now is we are just going to evaluate this limit. So we're going to evaluate the limit and then put it back into the composed function. Okay, so 2 plus of 1 over x minus 2. So then what is this limit? Well, this is going to 2 plus. 2 plus is a number that's slightly bigger than 2. So then if you kind of just think about it, slightly bigger than 2, so maybe 2.01. So 1 over 2.01 minus 2, that is 1 over 0.01, which is 100. And so basically, since we know that this is a rational function with a transformation of 2 to the right, this really is the function that looks like this. So then this limit is going to infinity. Now that we know that it is going to infinity, we're going to take this limit, which was the limit for g, we're going to put it back into our composed function. So limit as x goes to, remember we found the limit here, so then we're going to put it back into this function, but we're going to have to change x because we're not going to 2 plus anymore. We already evaluated 2 plus. We know that the limit is going to infinity, so then we're now going to evaluate x goes to infinity of this function. All right, this again requires that you remember how inverse function of tangent looks like. Inverse tangent function looks like this. If you don't remember, please take this time and memorize it. There are two horizontal asymptotes. One is at x equals pi over 4, and one is at x equals negative pi over 4. I'm sorry, not pi over 4, pi over 2. Pi over 4 is defined. And so when we're saying what's going on when x is going to infinity of the inverse tangent function, we know the answer is pi over 2. So this is the trick called change a variable. Basically what you're doing is you can't really evaluate the function all at once. So limit all at once. So what we're going to do is compose the two functions so that you can find the answer. Okay, so let me show you really quickly this one. So again, this function e to the 1 over x, you're going to think of it as a function within a function. So then the outer function you can think of is e to the x, and then the inner function you can think of it as 1 over x. And so this is limit. We're going to evaluate the inner function first because this will go through the inner function. So 1 over x as x goes to 0 minus is negative infinity. And then you take that negative infinity and you evaluate it with the outer function. E to the x is like this. When it's going to negative infinity, that is going to 0. So then the limit is 0.